Hi everyone and welcome back to Practice IB. This lesson is topic A1.4, translation. I want to start with one quick note. This whole topic is higher level students only. So if you're a standard level student, you don't have to do this. Feel free to move on. Higher level students, please stay with me. This topic answers a question you may have wondered about. When you write a program in Python or C, how does the computer actually understand it? Here's the important point. The processor inside your computer doesn't understand Python. It doesn't understand C. It doesn't understand any human language at all. It only understands machine code. Machine code is raw binary. It is just ones and zeros. So there must be a step in the middle. That step turns the code you write into the code the processor can run. We call that step translation. And translation is what this whole lesson is about. First, we will see a real example of code turning into binary. Then we will look at the two main methods. These are compilers and interpreters. After that, we will walk through the translation pipeline one stage at a time. Then we will cover the hybrid methods. And at the end, we will answer real exam questions together. Please keep one word in your mind in the whole time. That word is evaluate. It is the command term for this topic. It means you weigh the good points and the bad points, then you make a choice. Let's begin. Here's our plan for the lesson. The syllabus lists this as a single understanding, but there's a lot inside it. So we will go through it in clear steps. First, the big idea. We will see why source code cannot run directly. And we will look at the real example of one line of code turning into binary. Second, the two main approaches. These are the compiler and the interpreter. Third, the translation pipeline. This is the set of stages that code passes through. Most of these stages are shared by both approaches. We will trace a real line of Python through every stage. Fourth, the hybrid approach. These are the GIT compilation and the bytecode interpreters. Fifth, we will compare all four approaches and we will learn how to choose the right one for a given situation. Then at the very end, we will do something extra useful. I will give you 3 real exam style questions. You will try them yourself first. After that, we will walk through the answers together. So keep that word evaluate in your mind as we go. Now let's start with the big idea. Let's start with the most basic question. Why does code need translating at all? Look at the diagram on the left. At the top, we have source code. Source code is the program you write. You write it in a language like Python, Java, or C. For example, print open bracket koto, hello, koto, close bracket. That is very easy for a human to read, but the processor cannot read it. The processor is the chip that does the actual work. Now look at the bottom of the diagram. This is what the processor understands. It is the machine code. Machine code is pure binary. It is just patterns of ones and zeros. So the top and the bottom are very far apart. That is why we need translation in the middle. A compiler or an interpreter does this translation. Now let's look at the vocabulary on the right. The exam uses these exact words, so they matter. Source code is the program you write. Machine code is the binary that the CPU runs directly. In between these two, we have assembly language. Assembly language is a friendlier version of machine code. It uses short text codes called mnemonics instead of raw binary. For example, move means move and add means add. Finally, here's the idea that drives the whole topic. There are two ways to translate. A compiler translates the whole program first, then you run the results. An interpreter translates and runs the program line by line. So one method does everything at once. The other does it line by line. The single difference shapes everything else in the lesson. Now let's make it concrete with a real example. Let me show you translation actually happening. We will use a real example. This makes the whole idea much clearer. On the far left, we have a single line of higher level code. It says score equals 42. This is simple. We are just storing the number 42. Now follow the arrow to the middle. The one line becomes 3 lines of assembly language. Let's take them one at a time. The first line is LDR R1. This loads a memory address into a register called R1. A register is a tiny, very fast storage slot inside the processor. The second line is mov R2. This loads the actual value 42 into another register called R2. The third line is STR R2. This stores the value from R2 into the memory location that R1 points to. So the 3 steps are simple. First, find the address. Second, get the value. Third, put the value at the address. Now follow the second arrow to the right. Each assembly instruction becomes raw machine code. This is the binary you can see on the screen. It is just ones and zeros. And this binary is the only thing the processor truly runs. So look at the journey. One friendly line of code became 3 assembly instructions, and those instructions became binary. Here's one important note before we move on. This exact assembly and binary depend on the type of the processor. For example, x86, ARM, and MIPS are all different. This example uses ARM version 7. You will not have to write machine code by hand, but you should understand this journey. It goes from high level to assembly to binary. Now we reach the heart of the topic. We will look at the 2 ways to translate, side by side. On the left is the compiler. A compiler takes your entire program, it translates all of it into machine code before the program runs. The result is a separate file. We call this file a binary executable. You then launch this file on its own. Here is a simple way to picture it. Imagine translating a whole book from French to English. You translate it all, you print the finished English copy, then you hand it over. All the work is done in advance. So what are the advantages? First of all, it is very fast. This is because it's already machine code. There is nothing left to translate. Second, errors are caught at compile time. That means they are caught before it ever runs. Now the downsides. First, the executable is platform specific, so you must recompile it separately for Windows, for Mac, and Linux. Second, the development is slower. This is because you recompile after every change. Compiled languages include C, C++, Rust, and Go. Common compilers include GCC, Clang, LLVM, and Microsoft Visual C++. Now look at the right side, the interpreter. An interpreter reads and translates your program line by line as it runs. It doesn't produce a separate file. Here's a simple way to picture it. Imagine a live translator standing beside you. They translate each sentence the moment you say it. So, what are the advantages? First, you get instant feedback. This is because there is no compile step. Second, it is portable. It runs everywhere the interpreter is installed. Now, the downsides. First, it is slower. This is because each line is translated while it runs. Second, an error on a line is not caught until the program reads that line. Interpreted languages include Python, Ruby, PHP, and JavaScript. You might think that compilers and interpreters work in completely different ways inside. But here's a surprise. They share the same first 3 stages. Let's walk through them. Stage 1 is lexical analysis. The translator takes your source code, it chops into small, meaningful pieces. We call these pieces tokens. Tokens are things like keywords, variable names, and operators. Think of it like breaking a sentence into individual words. Stage 2 is syntax analysis. A component called a parser does this. A parser checks that the tokens follow the grammar rules of the language. It then builds a structure called a syntax tree. Think of it like checking that the words form a correct sentence. Stage 3 is a semantic analysis. This stage checks the meaning. Does the code actually make sense? It catches problems like type mismatches. It also catches the use of a variable you never declared. So those 3 stages are shared by both methods. They are lexical, syntax, and semantic analysis. After this point, the 2 methods go their separate ways. A compiler does 2 more things. First, it optimizes the code. This makes it faster without changing what it does. Then it generates a machine code executable. The program runs later as a separate step. An interpreter does something different. It generates bytecode. Then it runs that bytecode straight away, one instruction at a time. So the analysis is the same, the ending is different. Now let's watch a real line of code travel through all of these. Let's make the pipeline real. We will follow one line of Python through every stage. The line is print, open bracket, koto, hello world, koto, close bracket. Step 1 is initiate execution. You run the program. For example, you click run in your editor. Step 2 is lexical analysis. The line is broken into tokens. So print is a keyword, the brackets are operators, and koto hello world koto is a string literal. A string literal just means a piece of fixed text. Step 3 is syntax analysis. The parser checks that this is a valid function call. A valid call is a name followed by brackets with an argument inside. The grammar is correct here. Step 4 is semantic analysis. This checks the meaning. Does print actually exist? Can it accept a string? Yes, it can. And there are no type errors. Step 5 is code generation. The code is turned into Python bytecode. The bytecode is made for the Python virtual machine. Remember, bytecode is lower level and platform independent, but it's not machine code yet. Step 6 execution. The interpreter runs the bytecode one instruction at a time, and finally the words hello world appear on your screen. So this whole invisible journey happens every time you run even one simple line. Seeing it step by step is exactly the kind of detail the exam rewards. So far this sounds like a simple choice. You compile for speed or you interpret for convenience. But engineers asked a good question. Why not get both? This gives us two hybrid approaches. Let's look at the left side first. This is JIT compilation. JIT stands for just in time. It doesn't compile everything in advance, and it doesn't interpret everything slowly. Instead, it translates code into machine code at runtime. It does this right when the code is needed. Here's the clever part. When it sees code, then runs often, it compiles that piece once. Then it caches it. Caching means saves the fast machine code version. So the next time, that piece is already fast. This means a JIT program gets faster the longer it runs. The trade-off is a little slowness at the start, while it warms up. Java and C# works this way. Now look at the right side. This is the bytecode interpreter. Here the source code is first compiled into bytecode. Bytecode is an intermediate form, and it is platform independent. Then interpreter runs that bytecode. So there are two steps. First, source, then bytecode, then execution. The big advantage is portability. The same bytecode runs on any machine that has a compatible interpreter. This is how Java keeps it write once, run everywhere promise. Python's standard version called CPython works this way too. So remember the keyword for bytecode. It is platform independent. That is the main advantage, and the exam loves it. This is the slide to screenshot. It pulls everything together into 4 dimensions. These are the 4 dimensions you use when you evaluate. Let's read across them. The first dimension is error detection. The question here is simple. When are mistakes code? For compiled languages, mistakes are caught at compile time. So many errors are caught before the program runs. For the other 3, errors are mostly caught at runtime. That means while the code runs. The 3 are JIT, bytecode, and interpreted. The second dimension is translation time. A compiled language does all its translation in advance, so there is no cost while it runs. An interpreted language does almost no work in advance, but it pastes the code during execution, so it is the slowest to run. JIT and bytecode sits in the middle. The third dimension is portability. The question is, can it run anywhere? Compiled code is platform specific. It is locked to one type of system. Interpreted source code and bytecode are both highly portable. JIT is interesting here. It is bytecode is portable, but the machine code it makes is not. The fourth dimension is what each one is best for. Compiled is best for performance and critical apps. JIT is best for long-lived programs like servers. Bytecode is best for cross-platform software, and interpreted is best for rapid development, scripting, and web work. So learn these 4 rows. They are error detection, translation time, portability, and applicability. With them, you can answer almost any question on this topic. Let's put that into practice. Evaluate questions almost always give you a situation. Then they ask you to recommend an approach. The trick is simple. First, find what the situation cares about most, then match it. Here's a scenario 1. A startup wants to build a prototypes quickly. They write and change device scripts all the time. So the priority is development speed. They want to change something and see the result right away. So the answer is an interpreted language like Python. There is no compiler and cycle to slow them down. Here is scenario 2. A high-frequency trading platform must make trades in microseconds. So the priority is raw speed. Nothing else matters as much. So the answer is a compiled language, like C++. It runs as direct machine code. There is no translation while it runs. Here's scenario 3. A company builds a CRM system. It must run on Windows, Mac, and Linux, and it must do this from one code base. So the priority is portability. So the answer is a bytecode and GIT approach, like Java on the JVM. One set of bytecode runs everywhere, and the GIT keeps it reasonably fast. So notice the pattern in all three. First, identify the priority. Is it development speed, raw speed, or portability? The right choice then follows naturally. In the exam, state that priority clearly, justify your choice, and finish with a clear conclusion. That is exactly what Evaluate asks for. Before we reach the practice questions, let's clear up some common misunderstandings. These quietly cost marks, and some of them are sneaky. Number 1, compiler versus interpreter is not a strict either-or choice. Many languages uses both. For example, Python compiles your source into bytecode, then it interprets that bytecode. Number 2, GIT is not just a normal compiler. The whole point of the GIT is that it compiles at runtime, not before execution. Number 3, bytecode is not machine code. It's an intermediate platform-independent form. It still needs an interpreter or a GIT to run. Number 4, interpreted is not always slower in a way that matters. For short scripts, the difference is very small. The same is true for tasks that wait on input and output. Number 5, compiled is not automatically better. Development speed, portability, and the use case often matter more. Number 6, Java doesn't compile to machine code. It compiles to bytecode. And that bytecode runs on the JVM, the Java virtual machine. Watch that last one carefully. It's a very common exam trap. So run through this list whenever you answer a translation question. Let's gather our exam strategy before we practice. Look at the habits on the left. These are the habits that score marks. First, remember what evaluate means. You weigh the good points and the bad points, then you give a conclusion. A one-sided answer will not get you full marks. Second, know the 4 dimensions by heart. They are error detection, translation time, portability, and applicability. Third, 4 scenario questions. Identify the priority. Is it speed, development time, or portability? That decides your answer. Fourth, remember that GIT is hybrid. Say clearly that it combines interpreting and compiling. Fifth, always state when errors are caught. It is compile time for compiled languages. It is runtime for the rest. Sixth, remember the main advantage of bytecode. It is platform independent. And finally, have one example ready for each method. Use C for compiled, use Python for interpreted. Use Java for GIT, use CPython for bytecode. Now look at the command terms on the right. Evaluate is the big one here. It means weigh the pros and cons, then judge. Compare means give both similarities and differences. State means just give the facts. Outline means a short account of the key points. So always read the command term first, then answer exactly what it asks. Now let's test all of this with some real questions. Okay, now it is time to practice. Here are 3 exam style questions. I really want you to pause the video right now, try them yourself before I give the answers. This is the best way to find out what you truly know. Here's the question 1. It is worth 4 marks. Describe how a high-level instruction is translated into machine code. Notice the command term describe. It means state the key features, which are stages. Here's a question 2. It is worth 2 marks. Outline the role of a parser in the translation process. Outline means a short account. Here's a question 3. It is worth 3 marks, and it is the important one. Evaluate the use of bytecode in programming language translation. Evaluate means you weigh the advantages against the disadvantages. Then you reach a conclusion. So please pause now, grab a pen, write your answers. When you're ready, start the video again. Then we will go through the model answers together. Let's walk through question 1. Describe how a high-level instruction is translated into machine code. It's worth 4 marks. 4 marks means you want about 4 clear points. And we already have the perfect structure. It is the translation pipeline, so let's use it. Point 1 is lexical analysis. The source code is broken down into tokens. There are the keywords, identifiers, operators, and literals. That is 1 mark. Point 2 is syntax analysis. A parser checks that the tokens follow the grammar rules. It then builds a syntax tree. That is the 2nd mark. Point 3 is semantic analysis. The meaning is checked. Do the types match? Are the variables declared? Is the logic sound? This is the 3rd mark. Point 4 is code generation. If it is compiled, the code is translated into machine code. If it is interpreted, the code is translated into bytecode and then executed. That is the 4 mark. So you get 1 mark for each stage you described correctly in a logical order. And here's a way to make your answers even stronger. Add a short, concrete example. For instance, score equals 42 becomes LDR, MOV, and STR. And those become binary. This shows the examiner that you truly understand it. It shows you didn't just memorize it a list. Now let's do the question 2 and 3. Question 2 asks you to outline the role of a parser. It is worth 2 marks. The 2 marks means 2 points. Here's the first point. A parser analyzes the stream of tokens. It checks that they follow the grammar rules of the language. That is 1 mark. Here's the second point. It breaks the input into a hierarchical structure. The structure is a parse tree or an abstract syntax tree. It shows how the elements relate to each other. That is the 2nd mark. Keep it short and precise. This is because outline only wants a brief account. Now question 3. This is the evaluate question, and it is worth 3 marks. Evaluate the use of bytecode because it's an evaluate question. You need 3 things. You need advantages, then disadvantages, then a conclusion. Here is the first advantage. Bytecode is platform independent. The same bytecode runs anywhere with a compatible interpreter or a virtual machine. So it's highly portable. That is 1 mark. Here's the second advantage. Bytecode is more compact and more optimized than source code. So it runs faster than interpreting raw source. That is another mark. Now disadvantage. Bytecode still needs an interpreter or a virtual machine at runtime. So it is slower than fully compiled native code. And now the part that students forget. You must give a conclusion. Bytecode is the best choice when portability matters more than top speed. A good example is cross-platform application. Without that judgment at the end, you cannot get full marks on an evaluate question. And that is the topic A1.4 complete. And with it, the whole of Unit A1 is done. Really well done. Let's recap the 5 big ideas. Number 1, translation turns human-readable source code into machine code that a processor can run. The journey goes from high level to assembly to binary. Number 2, a compiler translates everything first, so the program is fast to run. An interpreter translates line by line, so it is fast to develop. Number 3, all translators share the same first stages. These are lexical, syntax, and semantic analysis. They only differ in what happens next. Number 4, GIT compilation and bytecode interpreters are hybrids. They trade a little speed for portability and flexibility. Number 5, When you evaluate them, use the 4 dimensions. These are error detection, translation time, portability, and applicability. If this lesson helped you, the worksheet for this topic is linked in the description. Go and test yourself. And for more practice questions and full walkthroughs, visit praxisib.com. If you are studying for IB Computer Science 2027, please subscribe so you do not miss the next unit. In the next unit, we will move on the networks. Thank you so much for watching. I will see you in the next lesson.